Now, if you remember that the functional form of the distribution function was a cube into e to the power minus bv square, and then we said that we are going to integrate it to get the entire probability, because by definition, since it's a probability distribution in the the velocity space, so if we integrate it irrespective of any direction, so that will give me the actual velocity or the total probability, and the total probability must be equal to 1. So if I integrate it over the entire volume, I should get it the value equal to 1. This volume, again, it is in the velocity space. Now, part of the dv that we have already calculated, we have already integrated it over the theta and phi, and we know how to integrate it, because this volume element was basically v square sine theta d theta d phi, and this integration means actually this is a triple integration between this v, theta and phi, v going from 0 to infinity, theta going from 0 to pi, and phi going from 0 to 2 pi. So those three integrations, I mean, out of those three, these two are done already. So all we have to do is to evaluate this integral 0 to infinity. So let me write the other values. So the integration over theta and phi gave 4 pi, and then there was a v square, and then we had a dv also, and we had basically f of v square dv. That we are going to evaluate, and that we know should be equal to 1. Now let us write the value of v square. So that will be, sorry, f of v, that is a cube. A cube also we can keep out of the integration, 4 pi a cube, and then we have e to the power minus bv square into v square into dv. Now for evaluating this integral, we can use a standard integration table, but I'll not use that. I'll rather actually tell you any general integral, how we can solve this kind of integrals. Now, what is this kind of integral? So suppose I have a very general integral, which is integral 0 to infinity x to the power n minus 1 e to the power minus ax, or better write the e to the power minus x first, x to the power n minus 1 dx. That is a special function, and this special function is known as gamma function. We write it as just like this, and the value of the integral will be gamma n by a to the power n, where this thing is nothing but gamma. It is basically gamma of n. We call it as gamma n, and the value of it is nothing but n minus 1 factorial. And if you by chance get gamma half, that will be nothing but root pi. And remember that 0 factorial is 1. I hope you know what is factorials. Now let us try to evaluate something. Let us say evaluate here. So here what we have, it is e to the power minus ax square into x square dx, some kind of thing. So suppose I ask you to evaluate this one, e to the power minus ax square. Let us first evaluate this one, e to the power minus ax square dx. What is the integral? Now what we have to do, we have to write it in this form, in this integral form, then only we can directly put the value. Now think about it, how to do it. First look at the exponent. What is the variable? The variable is x squared, not x. So here I have to write it, instead of dx, I have to write it as d of x squared. So we know that d of x squared is nothing but 2x dx. So I have to multiply by 2x and I have to also divide by 2x. So that is the idea. So what I'm writing, just follow carefully. I have e to the power minus, let me just write the dx first. So I'm writing that 2x dx, and then I have to use something like, or we can write the 2x dx later also, that's not a problem. So I have e to the power minus ax square into, I have 2x dx, that will give me the d of x square, and then I have to divide it by x, that I will write at x to the power minus 1, and I also have a factor of half because to account for this 2 here. So x to the power minus 1, now I have to write everything in terms of x square because x square is now the variable. So x to the power minus 1, instead of that I can write it as x square to the power minus half, because that is also x to the power minus half minus 1. But instead of writing minus half, I'll write it as n minus 1, because in the gamma function formula it is n minus 1. So minus half is nothing but half minus 1. So this entire thing, e to the power minus ax square, I can write it like this. So in the next step, what I'll do is that, and the x is going from 0 to infinity, so I'll write it as half 0 to infinity e to the power minus ax square, x squared to the power half minus 1 d of x square. You can easily do a change in variable. You can just say that x square is z. So when x is 0, z is 0. When x is tends to infinity, z is also tending to infinity. Okay. So you can just do a change in variable. So you can write e to the power minus az, z to the power half minus 1 dz. That's exactly the gamma function formula, and that tells you this value will be nothing but gamma n by a to the power n. So there is a half times gamma half by a to the power half. A is basically here. Let us just evaluate, say just e to the power minus x square, because this also will appear somewhere. So a is nothing but 1, so 1 to the power half. So the value of this integration will be gamma half is root pi, so it will be root pi by 2. Similarly, if you ask what will be the value of, say, x to the power e to the power minus x square, so that also we have to write in terms of gamma function. We can easily write it. So let us go back now and just try to evaluate this integral e to the power minus v square bv square v square dv. Now again, it is basically v square, so I have to write 2v dv, because in the next step I'll just write it as d of v square. So that is the trick. Now if I write it as 2v dv, of course I have to account for a factor half. I'm just writing this integrand right now. So this is and there are some constants also. So the limits are 0 to infinity, and then I have e to the power minus b v square. If I have 2v dv, so there is a v square already there. So suppose I have stolen one v, so this v and this v is v square. So that v, I can write it as v square to the power half, right? So and half, I have to write it as n minus 1. So that n will be basically half plus 1, or that I have to write it as 3 by 2 minus 1. So that now we can see how we have written it. Maybe I should write it in the next line. This was basically v, and then what I have is e to the power minus b v square to the power 3 by 2 minus 1. So 3 by 2 minus 1 is half, and v squared to the power half is v. So that's how we are writing. So it is nothing but half gamma 3 by 2 divided by b to the power 3 by 2. So gamma n by a to the power n. So here a is nothing but b, the constant. Then you can easily see what is gamma 3 by 2. So gamma n is n minus 1 factorial. That we will do. So here n minus 1 means actually, so let us go once again. So like suppose if I have gamma 5 by 2. So that will mean if it is n minus 1, so I can write gamma n is as n minus 1 gamma n minus 1, which is basically n minus 1 into n minus 2 into gamma n minus 2. So that will basically get a series which is nothing but n minus 1 factorial. So that's the same thing we're doing here. So if it is gamma 5 by 2, say for example, it will be n minus 1 gamma n minus 1. So n minus 1 is 3 by 2 gamma 3 by 2. Now gamma 3 by 2 will write it as 3 by 2 into n minus 1. So 3 by 2 minus 1 is half into gamma half, and we already know that gamma half means root pi. So it will be nothing but 3 by 2 into half into root pi. So in a similar token, this one will be nothing but half gamma half, which is, we have half here, we have another half, and gamma half is root pi divided by b to the power 3 by 2. So what we got is this half and this half gets 1/4 pi to the power half divided by b to the power 3 by 2. So now you can just put it here. Just for space, I'm just writing it here. It is basically 4 into pi into a cube into 1/4 pi to the power half divided by b to the power 3 by 2. That is equal to 1. Let me first simplify and then we'll equate it to 1. And then what we see here, this 4 cancels, and then what I get is nothing but pi to the power 3 by 2, because pi is nothing but pi to the power 2 by 2. So I can write it as a cube into pi to the power 3 by 2 divided by b to the power 3 by 2. That is equal to 1. Or we could actually write, instead of a cube, we could write actually b by pi to the power 3 by 2. So the distribution function is now slightly better. I can see that. So we are writing it as fv, the functional form of fv, which was this. So now I have written in terms of only one constant. So I have eliminated a. I'm writing a in terms of b. But still I have to evaluate b. b to the power 3, b by pi to the power 3 by 2, e to the power minus b v square. So that is now the distribution function. Now we have to evaluate b. Now to evaluate b, now you can ask, remember that we said that we will also take help of the fact that average value of the v square will be nothing but equal to the 3 kBt by m. So which we just started. So we'll just use this fact from the kinetic theory of gases, that v square average is 3 kBt by m. So now how will you calculate v square average from this function? It is very easy. So average value of any quantity, say in this case v square average, will be nothing but you take the v square, you multiply it by the probability factor, okay, and then you integrate over the v, and of course you have to integrate over everything, but the 4 pi is already there, so I'm just writing it like this, 4 pi, and I'm writing it as dv, and only integration over v. So what I get here is that let us just evaluate it. I have 4 pi, and then f of v, we got already an interesting relation, which is basically this one, b by pi to the power 3 by 2 a to the power minus bv square. So b by pi to the power 3 by 2 e to the power minus v square into v square dv, that integral. Now we can easily write this form, that it is e to the power minus v square. I have to write 2v dv for d of v square, and then I'll have one v here, one half here, and instead of v I can write v square to the power half, which is basically this here we had a v squared dv, because the volume element was 4 pi v squared dv, and together I'll have v to the power 4 dv, so I'll have a v cube here. So the v cube thing, I have to write it as v squared to the power n minus 1. So if I write it as v squared, it is basically v squared to the power 3 by 2, and the 3 by 2 I can write it as 5 by 2 minus 1. So that is the entire thing, 0 to infinity, and there are some constants, which is 4 pi into b by pi to the power 3 by 2. So this thing will be nothing but gamma 5 by 2 divided by a to the power 5 by 2. Now also have to write the b here, because in the distribution function there was a b. So it will be b to the power gamma n by a to the power n, b to the power 5 by 2. Now you can easily see we're going to get a very interesting relation. So I have 4 pi here, b by pi to the power 3 by 2 into half. Instead of gamma 5 by 2, you can just directly write down the value. So gamma 5 by 2 is 3 by 2 times half times root pi. And then let us see what we discovered. So this half and this half gets cancelled right away. Sorry, it's not cancelled, it will be the value. So let us see actually what we get. So what we have here, let's just write everything together. I have 3 here, and 2 into 2, 4, and 8. So that 4 actually gets cancelled with this 4. So ultimately I'll have 3 by 2, and it is basically 2 into 2, 4 into 8, and let me just write it, 4 into 3 by 8, so it is 3 by 2. And then just calculate the pi's. So I have pi divided by pi to the power 3 by 2, and pi into pi to the power half is pi to the power 3 by 2, and that gets cancelled with pi to the power 3 by 2, so that is fine. I have b to the power 3 by 2 and b to the power 5 by 2 here, so that gets cancelled. I'll have only 1 over b, and that should be equal to, as you know, it will be 3 kBt by m, because that's the value of the v square average. So we get, what is b? B is nothing but we get 3 and 3 cancels here. Basically I'll get twice kb, or we can just go the other way. So this is the value of B. So the distribution function f of v. Now instead of f of v, we are writing every time as what is the exact distribution function, but then when we are integrating it, with v and v plus dv. So what we are writing from, or what we'll write from now onward, we just introduce a new distribution function. So this is nothing but the distribution of velocities or distribution of speed from v to v plus dv. So that we can get, so f of v dv is nothing but, I have to take the original thing fv and integrate it only over the theta and phi, and with the corresponding volume element, but that will give me and without integrating it over v, because we are in only the v part and just integrating over the theta and phi. So theta phi integration gives me 4 pi v square dv. So we are just writing it as 4 pi fv dv. There is also v square dv. So the v square value, now we can write it. What was f of v? F of v was a cube, but a we wrote in terms of b already. So we found that it is b by pi to the power 3 by 2. Now b is twice m. So we can write it as just 1 minute, it will be 3 by 2 and it will be actually b will be m by 2 cavity. So let us just rewrite it once again. F of b is b by pi to the power 3 by 2, b by pi, so it will be 2 pi kbt to the power 3 by 2 into e to the power minus b v square, b it will be m v square by twice kbt. So this distribution function which we are going to use, which is already integrated over theta and phi, will be nothing but 4 pi into m by 2 pi kbt raised to the power 3 by 2 into e to the power minus m v square pi twice kbt into v square dv. So that is the Maxwell-Boltzmann distribution of molecular speed. So this is the Maxwell-Boltzmann distribution of molecular speed. It's not velocity again. So what we learned today, or what we discussed today so far, is that we started with kinetic theory of gas, and then we said that no, actually that is not the gas molecules have a range of velocities. It is not that every molecule is having the same velocity. And then we argued that on a statistical ground, within a range of velocities, the number of the molecules will be the same, and that's what exactly we wanted to calculate. Now when we are talking about velocities, actually the thing which we measure is speed, and speed is independent of any direction, and which means from a velocity distribution we can construct speed distribution just by integrating over the direction, which means actually we are removing the constraint on the direction. It is not biased in moving in any particular direction. And then we showed how to get the volume element in spherical polar coordinate. And we before that, prior to that, we actually discussed the actual form of the distribution function, based on several logical footage where we said that it should be an even function, it should vanish at plus minus infinity and all these things. And then we got a distribution function, small f of v. That distribution function is a probability function, and then f of v depends also on different direction. But we said that we better actually get a distribution function where we are integrating it over all the direction, and all we are getting is basically the final Maxwell-Boltzmann distribution, where the directional independence thing is already taken care of. We have already multiplied it by 4 pi v squared into dv. So all we have to do is take this function, multiply with something, say some average quantity that we want to measure, and then integrate only over v, because the theta phi integration is already done. So all we have to do, suppose for example, which we'll see in the next part, is that if we integrate, if we want to find the value of average velocity, what we have to do, we have to take this velocity and ask what is the probability, just multiply it by the probability distribution, and then just integrate over 0 to infinity, and we'll get something. So that we'll see. And we have not plotted the Maxwell-Boltzmann distribution yet. We will first plot this function, how it looks like, and we'll also discuss that what are the how to go from the speed distribution to the energy distribution. So those things we'll discuss in the subsequent parts. Thank you.